Hey, it's Mr. K doing a video for AP Physics 2. We're going to talk a little bit about electrostatics, a little bit about electrodynamics here. And we're just going to start off with a charge. So here's empty space, and I just dropped my ruler. But here's empty space, and we're going to plop down a charge here, and this charge is going to be some plus Q charge. I don't know what it is, it's just there. So we plop it down. What you know about charges right now is that like charges like to repel, opposite charges like to attract, but here's empty space. When we plop this charge down, there's nothing there, which means it takes nothing to put it there. There's no resistance, there's nothing to fight, there's nothing that will pull it there in the first place. Now that we place this charge here, what happens is that there is an electric field that's all around, it permeates all around it for infinity. And this electric field goes out in all directions. It goes up. It goes down. How many squares do we do? 1, 2, 3, 4. It goes down. It goes left. It goes right in all directions, everywhere. And these arrows do not, or these vectors do not give it justice at all. It goes out in all directions. Let me get that measurement correctly. About 2.5. So it goes like that. Goes down like this. All directions are going to be considered for your electric field lines. And there you go. So going out in all directions, great. This is the electric field. Do a little E with a hat on it. And the electric field strength is going to be, well, it comes from Gauss's law. And what Gauss's law is, well, it says, it talks a little bit about flux, and flux is like this amount of stuff that goes through an area. So Gauss's law says, hey, let's take an amount of flux, this fluxy symbol, and we're talking about electric flux. So we're talking about the electric field going through some area A. Well, that's going to be equal to the charge that's creating that flux divided by this thing that we call the permittivity of free space. Now there's another one called the permeability of free space, and that's what we're going to use for magnetic fields. Magnetic fields, electric fields, different properties with space. You might ask why this, why that, but at the end of it, you need to think it's just a property of the space, the universe that we live in. So here we have Gauss's law, and this electric field at any distance away should be equal to this strength based on the area of whatever you're trying to enclose. So this is going radially outwards in all directions, not just up, down, left, right, but also like forwards and backwards. So this goes out in a big sphere. And so we're going to call that a 4 pi r squared, because that would be the surface area of this imaginary sphere that's around it, that's enclosing this charge Q. And I just smudge that, and that's equal to Q over epsilon naught. So the Q that you enclose by this area, epsilon naught. Well, that means that we have 1 divided by 4 pi, I'm going to move this epsilon naught over a little bit, Q divided by r squared. Okay? And in class, we would have already mentioned this, but this 1 over 4 pi epsilon naught, that's K. That's going to be 9 times 10 to the 9th. So, good value to know, K, 9 times 10 to the 9th, and that's going to be Newton meters squared over Coulomb squared, I do believe. So, or Newton meters squared over Coulomb squared. Yeah, that should work out, because this is going to be newtons per coulomb. Yeah, that'll work out. So that's going to be KQ divided by R squared. So this is your electric field formula. All right, this is one of the basic ones. Now there's another one out there called Coulomb's law, which comes pretty much from this, but it's what if you were to put another charge out here? What if? And to put that charge there, let's say it's another plus Q charge. Well, now these two charges are interacting. You place them in the electric field of the other. Well, what do like charges do? Well, they like to repel, because you place it in the electric field of the other guy. So we place this Q charge here. The electric field at this location is going to the left. It wants to push this positive charge to the left. There's a force there. Turns out there's another thing called Coulomb's law. You might have learned it in chemistry, but Coulomb's law talks about the force between charges, and we get this force, and this force is a vector, and my bad, keep the vector symbol there if we can. I'm going to forget about that eventually, but the force between these two charges is going to be this K constant that we just got over here, and it's going to be Q1 times Q2, the other guy, divided by R, the distance between them. We're going to square that. All right, so all this is we're taking the electric field. If you notice, this is the electric field formula. And we're just multiplying it by another Q, the Q that we place inside of that electric field. That's going to give us a force. In this case, the force is going to be repulsive. So we know that the plus Q is going to go pushing to the left, and the plus Q over here is going to be pushing to the right. It's going to tell you the strength of it, but it's kind of your job to figure out which way it goes. Okay, so you place this charge here, and the other thing that you could think about is that in the beginning we said, hey, this was empty space, but now that this charge is here, how the heck do we place this charge over here? Because shouldn't this one that's already there resist the charge that we're trying to place over here on the left side? And the answer is yes. So to bring this charge in from infinity, we need to push it there. Okay, and we need to push it for a distance there. And if we're pushing for a distance, then that requires a certain amount of work to be done, which is interesting. Remember that work is a force for a distance. It's also a change in kinetic energy if we can. So really, if you thought about this, if this charge is here and this charge is here, if we let them go, they're going to push each other apart. And there's going to be a gain in kinetic energy because there is a potential, some electric potential here. And the way that we would look at that is we would just take this formula and we'd say, all right, there is a distance that we can push it. And we're going to multiply that by the R, this distance between the two. And so the electric potential energy is equal to this force times this distance that's between them. And you're going to be like, why is that? Well, as these two get pushed apart, this force starts to decrease, and we can shoot them off to infinity. But what really matters is how close they are right now. And that force, that KQQ over R squared times R, that's going to give us KQQ12 over R squared. We're going to multiply that by the R. That's force times distance. And that should equal our electric potential energy. That's going to be K Q1, Q2 divided by R, the distance between these two charges right now. So that would be the electric potential energy of these two. It's like you're in a gravitational field and you have this distance to fall. Well, these two have the distance to repel. If they were negative charges, yeah, they would fall together. They'd gain some speed by doing that. Okay, so that kind of begs the question: what like if this charge wasn't here, there should be this potential that's around it, kind of like the Earth, right? The Earth has this gravitational field, and although nothing could be in it, it's still there. And we know that if we place something in it, that something is going to want to fall down. It's going to want to be pulled towards the Earth. Well, if we were to look at this charge, anywhere around this charge, there could be some inherent potential, no matter where we talked about, out here, in here, over here, anywhere. And so, really, what we would talk about is this thing that we call potential difference, or potential, or electric potential, and that the word that we're looking for is voltage. So voltage, really, we should be talking about that as electric potential. Okay, and when we put the charge in there, it becomes electric potential energy. But voltage is going to be KQ over R, Q being the charge that's creating that potential. It's kind of like the Earth. So here we have three formulas. One is a formula of force. Two charges, there's a force between them. These forces are vectors. Kind of used to working with that. We have another equation for the field. How strong that electric field is. You place the charge inside of that electric field, it gets a force. All right, and then there's this other thing that we consider that called potential, and that's like having a cliff, and there would be a distance for you to fall if you placed a rock at the top of that cliff. But if you placed a boulder at the top of that cliff, not just a small rock, there would be more energy involved, and that would be like putting more charge here. There would be more energy involved when these want to push apart and come together. So these three equations, KQ over R squared, KQ over R squared, or KQ over R, are very important for electrostatics. Now, if we were to consider what goes on whenever we try to put charges next to each other, let's create a new scenario. And again, this is empty space. So if this is empty space, let's say I plop a charge down here. That's going to be 4 coulombs of charge. and it's going to be plus 4 coulombs of charge. It would take nothing to move that charge there. Okay, but let's say I want to place another charge. Let's say 1, 2, 3, 4 right here. And I wanted to place the charge over here that's going to be, let's say a negative 4 coulombs of charge. Well, to place this charge here, negative 4 and positive 4, they want to attract. So basically I can just let that go. But if I wanted to place it right here, I'd have to slow it down, right? So I'd have to do negative work on it to slow it down and have it stay there, because it wants to speed up. It wants to fall into that location. It wants to fall into this guy, actually. So we want to pull it back, hold it still. Okay? So it's going to take me some energy to slow it down. Whereas if I put a positive charge here instead of negative charge, I would have to push it there to actually get it there. And so the equation I'm looking at is this one. And so to create the system of just the 4 Coulomb charge cost me nothing. But to create the system of the plus 4 and minus 4, now we're talking, it's going to take KQQ over R amount of energy. This is joules to create it. So placing this one here, nothing. Placing this one, it would be KQ4, first Q, second Q, negative 4, over R, and let's say this R is 1, 2, 3, 4 meters on the bottom. So that's just to place this charge here. What if I wanted to place another charge right below this guy? So 1, 2, 3, 4. Let's place another 4 down here, 4 meters. And let's put another charge there. Let's call it a negative charge as well. Negative 4 coulombs of charge. So to place this one here, well, these two guys were already in the system, so I got to fight this guy. Actually, wait. This wants to be here because of this positive charge. But due to this one, I need to actually push it to be in the vicinity of this negative charge, because, you know, opposites attract, likes repel. So let's talk about this first one first. We have to do another amount of energy here, which is going to be KQ, first Q, that guy, over R. Okay. And then there's got to be the consideration of these two, which is going to be K, Q, Q over R, which is not going to be 4. It's going to be 4 times the square root of 2. So square root of 2 times 4. All right? And so what you should notice there is that these negatives cancel out, which means that there's a positive amount of energy that's required to push these together, which means it's kind of like a spring that's going to want to spring apart and blow apart. Well, let's put one more here. Bottom right corner. Let's do the positive 4 plus 4 charge Q. And you're going to say, oh, crap. Well, if we had to do 2 for this one down here, we got to do 1, 2, 3 for this guy over here, and that's true. And so let's place this charge here, and let's talk about what's going on with these two. So we're going to have to do plus K, Q, negative 4, Q, charge that we placed there, divided by the distance between them. And we got to do this one here. So, you know what, I'm just going to double that up. Exactly what I just did. And then I got to consider that these two, I have to push them together. So I got to add in some K, Q1, Q2 over the square root of 2 times 4. So this distance here, if we had a side 4 and a side 4, that's going to be 4 squared plus 4 squared square rooted. So square root of 2 times 4 should work out. And yeah, that's the total. So this would be the amount of electric potential energy that I would need to create this system. And you're like, that's weird. But what's great about about electric potential energy is that energy is a scalar, so you don't care about direction. All you really care about are signs. And so what we can say here is that, ooh, look at this. We can say that's gone, that's gone, that's gone, that's gone. That's positive now, right? That's gone, that's gone. That's gone, that's gone. That's gone, that's gone. And we have K all throughout, so I'm going to say K, pull that out. First one I have a negative 4, plus another negative 4, plus 4 over square root of 2, plus -8. Ooh, that's weird. Plus 4 over the square root of 2. Okay? And so if that's the case, I have -4, -4. That's going to be -8. That's going to be -8 there, so -16. And then I've got plus 8 over the square root of 2. And then is there some kind of good math that I can do? I don't know. Let me just plug it in. So -16 plus 8 divided by the square root of 2, square root 2. Not answer, 2. And I get a value of -10.343 times K, because that was on the outside, and this is going to be in joules to create this system. K's, well, that's not kilojoules, let's just make that clear. So K is 9 times 10 to the 9, let's just go ahead and multiply it. 9 times 10 to the 9, there we go. So negative, holy crap, 9.31 times 10 to the 10th joules of energy, but it's negative, okay, which means that this thing wants to fall together in the first place instead of blowing apart. All right, interesting. So each one of these is going to still be in the electric field of the other. This guy in the top right corner, it's negative. It wants to be attracted to this guy. It wants to be attracted to this guy. It wants to go towards these two. These guys over here want to be attracted together. The ones that are diagonal want to be pushed apart. But because of the r squared value on the force, looking like they want to be attracted more than repelled, and so really this system wants to collapse in, and we would have to take energy out in order for it to stay as is. Now, if we talked about the very middle of this, the very center of this, there's nothing there, but we can talk about the electric field at that location. The electric field, due to these two charges, would be down to the right, away from this guy, up and to the left, away from that guy. Those two would cancel out. The electric field from these two charges would be towards the bottom left and towards the top right. Those two would cancel out. There would be no electric field at the center. Okay, that's kind of odd. There would be, if you placed a charge there, there would be no force on that charge. And there would be no wantingness for it to move. There would be no voltage there either. It would actually be free to place a charge at the center, which is not true for other systems. So if we just considered another system that's much like the system that we just drew, except that maybe we had plus 4 coulombs of charge, plus 4 coulombs of charge, negative 4 coulombs, and negative 4 coulombs, well, at the very center, it would still be 0 volts, okay? For kq over r, kq over r, kq over r, kq over r, we can add all those kq over r's together. All the r's would be the same amount, but all the q's would start to cancel out. There would be 0 volts there. There would be 0 resistance to putting a charge at the very center. But once that charge was there, that charge, being positive or negative, would want to move either up or down due to these. So these two would create an electric field that way and that way, which in total would point downwards. And these two would create an electric field that way and that way, which would still point downwards. So it would be twice as big. So if you were to put a charge in the middle, it would be free to put it there. However, there would be a net force on it downwards because you're placing it in an electric field. We'll cover more of this. This is just a bit of a generalization of how to look at these three formulas and treat the addition of charges as you try to build a system. But definitely in class we will talk more and more about this. This is a pretty important part of the electrostatics unit. We'll stop it there.